Welcome everyone to this series of lectures on an introduction to linear regression. And this specific series starts out with theory revolving around the algorithm. In part one, we'll talk about history and motivation behind linear regression. As I mentioned, before we do any coding, what we want to do is have and build out an intuition of the theory and motivation behind linear regression. Specifically, we're going to start by understanding the brief history behind linear regression, linear relationships, and what they look like mathematically. Then we'll specifically talk about the ordinary least squares method, and move on to discussing things like cost functions, minimizing a cost function with gradient descent, and then vectorization. If you're interested in the relevant reading sections in ISLR, you can find them under Section 3. In general, the entirety of Section 3 covers linear regression, but what we're talking about right now just falls under 3.1, simple linear regression. I'd highly encourage you to read up the sections as we go along here in the slide presentation, because it will make your understanding a lot more robust. Okay, let's talk about the history of the invention of linear regression. And to put it simply, it is a bit muddled. But what we can do is understand the motivation behind developing linear regression. In general, linear regression methods, as well as the mathematical groundwork for them, grew out of a need for mathematically improving navigation methods based on astronomy during the Age of Exploration and after the Age of Exploration in the 1700s and early 1800s. Essentially, when you have ships out in the ocean, what they're using for navigation are star positions, basically astronomy. And a lot of mathematicians in this era are using mathematics to understand the movements and shapes of stars, moons, and planets. The mathematical groundwork begins in 1722, when Roger Coates discovers that combining different observations yields better estimates of the true value than just a single observation. Essentially, this falls back in line with what we know about things like that classic house price example. We know we should probably take different observations of houses that have sold in the past, instead of just relying on a single house that was sold. Then in 1750, Tobias Meyer also explores averaging different results under similar conditions in studying librations of the moon. And essentially, if we go back to our housing data and think about what that means, it's that the combining of different observations should also be done under similar conditions. That is to say, while the observations are different, in general, the conditions behind them should be similar. So we shouldn't just pick houses from all over the world. We should probably be picking houses from roughly the same city or same neighborhoods. This is later developed in 1757 by Roger Joseph Boskowitz, further developing combining observations when he's studying the shape of the Earth. And in 1788, Pierre-Simon Laplace develops similar averaging theories in explaining differences of the motion between Jupiter and Saturn. So lots of motivation here behind astronomy use cases for linear regression. But so far, we actually just have the mathematical groundwork. No one's technically, at this point in time, published linear regression. That changes in 1805 with the first public exposition on linear regression with least squares method. And it's published by the mathematician Adrien-Marie Legendre, who you may have heard of if you ever study things like Legendre transformations. Now, so far, you may be thinking that the timeline and history we just presented here is not actually muddled or confusing. We could see a clear mathematical groundwork being laid, discussing observations and averaging observations under similar conditions to the eventual first public exposition of linear regression by Legendre. But this is where it starts to get a little confusing. First off, the portrait shown here of Legendre was the most common historical textbook picture of Legendre for many, many textbooks. However, in 2005, it was discovered that this side portrait of the mathematician Legendre is actually a politician of the time named Louis Legendre. So this picture that was in almost every textbook image of the mathematician Legendre was discovered to be a picture of a totally different person. Stranger still, there's now only one known sketch that we know is of the mathematician Legendre. And it is a watercolor caricature of him that looks like this. Now you may be thinking, well, the issue of the portrait doesn't really affect the timeline of the publications. Well, this is where it begins to get even stranger. Years after Legendre's publication, in 1809, the very famous mathematician Carl Gauss publishes his methods of calculating the orbits of celestial bodies, showing linear regression with least squares method. But Upon publication, Gauss claimed to have invented least squares years before Legendre's publication, claiming to have invented least squares back in 1795, and decided not to publish it because he thought it was so trivial and obvious. What's really interesting is that Gauss was born in 1777, which means if he actually discovered it in that year, it would have made him 18 years old at his proclaimed time of discovering and inventing linear regression. Keep in mind, this is actually not too unrealistic, given that Gauss was a child prodigy in mathematics. It gets even a little weirder because 1 year before, in 1808, Robert Adrian published his formulation of least squares. So whatever the case of invention may be, whether Gauss discovered it and invented it first, or Legendre was the first one to develop it in his publication, what we really care about is building an intuitive understanding of linear regression. So let's talk about it. Put simply, a linear relationship implies some constant straight line relationship. The absolute simplest possible would be something like y is equal to x. So here, I can see the dots pointing out observations where y is equal to x. So x is 1, 2, 3, and the corresponding y values are then also 1, 2, 3. We could then, based on those 3 real data points, build out some sort of theoretical relationship like y is equal to x. Technically, I don't actually know if this is the true relationship between these 3 points, but I can see that it essentially has a perfect fit. That implies for some new x value, such as x is equal to 1.5, if I decided my fit of equation was y is equal to x, then I could predict the y is also 1.5 for an x of 1.5. But what's going to happen with real data is it's not going to fit perfectly on a straight line. So what we have to do is decide where do we actually draw this line of best fit. We could draw it like this, or maybe like this. We need to decide what here is going to be the best fit for real data. Fundamentally, what we do understand is we want to minimize that overall distance from the points to the line. So if I draw my line like this, notice I'm actually quite off the real points. And we can measure this error from the real data points to the line, and it's known as the residual error. So clearly, I want to try to minimize this residual error. So some lines will be better fits than others. And we can also see that residuals can be both positive and negative. Ordinary least squares works by minimizing the sum of the squares of the differences between the observed dependent values, that is, values of the variable being observed, in the given dataset and those predicted by the linear function. This is just the most formal way of saying that if we take a look back at this line and the residual errors from the real data points, what we're trying to do is minimize the squared error. So often we visualize the squared error with actual squares there, because if this line represents the error from the real data point to my fitted line, what I want to do is minimize that squared error. Later on, we're going to discover why we actually choose squared error. It makes the mathematics work out very nicely for us, especially when taking things like the derivative. So, as I mentioned, having a squared error will help us simplify our calculations later on when we're setting up a derivative for the purpose of minimization. What we're going to do is continue exploring ordinary least squares by converting a real data set into mathematical notation. And then later on, we'll see that we'll have to move beyond just simple ordinary least squares to talking about things like cost functions and minimizing them with a gradient descent. So that will help us work to solve a linear relationship between features and a variable. All right, I'll see you at the next lecture.